Hello, in this video we will talk about the Gauss Jordan elimination method. This is the method which is used to solve the system of linear equations. Suppose you have a system of linear equations and there are m rows and n variables. Then I told you that you can find a matrix AX is equal to B. You can always write the system of linear equations in matrix form, where A is the coefficient matrix and B is the constant matrix and X is the variable matrix. Okay, so if we write A augmented with B, and if we write A augmented with B, and this is the matrix which is called augmented matrix, the matrix augmented by the coefficients and the constant matrices, then we can apply the Gauss Jordan elimination method to convert this matrix into row reduced echelon form to find the solution. And this method is called Gauss Jordan method. So what are the steps here? The first step is augment the matrix, the coefficient matrix, with the constant. Okay, that means in the standard form you have A augment with B. Okay, so the next step is to perform row operations to convert this bigger matrix into row reduced echelon form. Okay, so we have to perform row operations to convert this augmented matrix into row reduced echelon form. Okay, so when you are trying to convert this matrix into row reduced echelon form, that means definitely first of all you have to convert it into row echelon form, and then you will reduce it. Then you will make the top non-zero entries into zeros. Okay, so the last step is read the solutions directly from the row reduced echelon form. Row reduced echelon form. These things will be clear when we solve an example. So here is an example. We are given a system of linear equations. So this is the system of linear equations. We have to solve it by Gauss Jordan elimination methods. Okay, in order to solve this system by Gauss Jordan method, we have to follow these steps. So first of all, I have to augment the coefficient matrix with the constant matrix. What is the coefficient matrix? The coefficient matrix is formed by the coefficients 3, 1, 4 and 1. Then there is no y here, so 0, so -1. Similarly, x is 0, 2, -1. Okay, so I will write the coefficient matrix as 3, 1, 4, 1, 0, -1, 0, 2, -1, because the coefficient of x is 1, the coefficient of y here is 0, so the coefficient of z is -1, so that's why this row is 1, 0. And the last row, there is no coefficient of x, so that means coefficient of x is 0, and then -2 and -2 and -1. Okay, so this is the coefficient matrix, but we have to augment this coefficient matrix with the constant one. So the constant matrix is this one, 9 -1 -6. So I will write 9 -1 -6 here. So this is the matrix which we will consider, and then we will proceed our steps. We will go to the next step. The next step is perform row operations to convert this into row reduced echelon form. So once we have this matrix, we can perform row operations to convert this into row reduced echelon form. In my previous video, I have explained very well that how can we convert a matrix into row reduced echelon form. There are multiple steps. I have explained there in the previous video. If you have not seen, you can watch. So the rough idea is, first of all, we have to find the leftmost non-zero column. So here the leftmost non-zero column is this one, and this column is called the pivot column. And the next step is to check whether the topmost entry is 0 or non-zero. If it is non-zero, then it's okay. Since this is already non-zero, so we will go to the next step. So the next step is make this non-zero entry 1. How can we make this entry 1? Okay, so there are multiple ways. So the first way, easy way, is to divide this row by 3. Otherwise, I can interchange these two rows so that I can get here 1. I will choose the second way. I will swap these two rows so that I can easily get here 1 and here 3. Why I am choosing the second way, not the first way? Because if I divide the first row by 3, here I will get 1 by 3, 4 by 3. These are the fractions, and it is hard to do things with fractions. So we have to avoid the fractions, okay, to keep our things simple. Okay, so I will swap the first row with the second one. So I have swapped the first and the second row. Now here we got 1. So this is the pivot entry. Now the next target is to make everything below 0. Since this is already 0, so I have to make here 0. Here, how can I make 0? I will use this pivot entry. So I will use this pivot entry to make this 0. How can I make this 0? If I write 3 minus something times pivot entry, since the pivot entry is 1, okay? So the obvious answer is 3. Since this 3 comes from R2, this is the scalar, and this is coming from the pivot entry. Pivot entry is in row 1. So this is the operation which I will perform now, okay? So I will perform R2 minus 3R1. So I have to make changes in the second row, okay? So the first and the last row will remain the same because I have to make this entry 0. So I have to make changes here. So I have written the first and the last row as it is. I will make changes in R2. These are the changes which will be made in R2. So what are the changes? What I will write? I will write R2 first. What is R2? 3, 1, 4, 9. I will write 3, 1, 4, 9. Then minus R3. So minus 3, I will write 3 everywhere. Minus 3, minus 3, minus 3. Okay? Times R1, minus 3 times R1. So I will write times something, times something, times something, times something. R1 here is 1, here R1 is 0, here R1 is minus 1. I will write minus 1. Here R1 is again minus 1. If I simplify, I will get this matrix, okay? So the second row will be this one. Now the next step is to write the submatrix using the current pivot entry. Since our current pivot entry is this, if we skip this and this, the submatrix is this one. We will repeat the same procedure for this submatrix. First of all, we will find the non-zero, leftmost non-zero column. So the leftmost non-zero column is this one in this submatrix, okay? And in this leftmost non-zero column, we will check whether the top entry is non-zero or zero. We can check the top entry is this one because this is the column, okay? So, okay, which is non-zero. Then the next step is make this entry 1. So since this is already 1, so nothing to do with this one. So we will circle this thing because this thing is very important. This is called the pivot entry, the new pivot entry. So now my current pivot entry is this one. Okay. The next step is eliminate everything down below the pivot entry. So the below the pivot entry is 2. I have to eliminate this. I have to make it 0. How can I make it 0? If I write 2 minus something times the pivot entry is 1. That means this 2 is coming from R3 minus, by the way, here I have clearly 2. Okay, minus this 2 is coming as it is, and this 1 is coming from the pivot entry R2. So this is the operation which I'll perform, R3 minus 2 R2. And these changes will be made in this row because I have to make this 0. So the first 2 rows will be the same. So what to do? I will perform this operation. First I will write R3. R3 is 0, 2, minus 1, minus 6. I will write 0, 2, minus 1, minus 6. Then minus 2 times R2. First of all, I will write minus 2 everywhere. Minus 2 times R2. What is R2 now? R2 is 0, 1, 7, 12. 0, 1, 7, 12. I'll write 2 times 0, 2 times 1, 2 times 7, and 2 times 12. Now I'll simplify. So after simplification, I will get this thing. Okay? So we have done with this pivot entry. Now we will again look at the submatrix. Now the submatrix is this one. We will check what is the leftmost non-zero column. So the leftmost non-zero column is this one. Since this is non-zero, I have to make it 1. How can I make it 1? Now there is only possibility to divide by minus 15. How can I divide this row by minus 15? It's very simple. Just divide by minus 15. So I have divided R3 by minus 15. So my new R3 is this one. Okay. So after simplification, I will get this matrix. Okay. But since this matrix is not in the row reduced echelon form, because this is our pivot entry, this is our current pivot entry, I have to make everything above 0 also. Okay, how can I make the things above 0? Here we can make 0 by using this pivot entry. How? 7 minus something times the pivot entry, and this something is obviously 7. That means this 7 is coming from R2 minus this 7 is constant, and this 1 is coming from the pivot entry, and the pivot entry is R3. Okay, so this is the operation which I'll apply here. So I'll apply R2 minus 7 R3. How can I write? R2 is 0, 1, 7, 12. So I will write 0, 1, 7, 12 minus 7. So minus 7 everywhere times R3. R3 is this is R3, so I will write 0. This is R3, so 0. This is R3, so 1. This is coming from R3, so 2. That's done. So now I will make here 0 also, because this and this both entries must be 0. So how can I make this 0? Because this is minus 1, so plus 1 times 1. So what will I write? This minus 1 is coming from R1, plus this 1 is scalar, and this 1 is coming from the pivot entry. So and the pivot entry is in the R3. So this is the operation which I'll perform for R1. Okay, so first I will write R1. R1 is 1, 0, minus 1, minus 1. I will write 1, 0, minus 1, minus 1. Plus 1 times R3. 1 times R3 means just R3. Just add R3. R3 is 0, 0, 1, 2. So plus 0, plus 0, plus 1, plus 2. If I simplify this, I will end up with this matrix. And this is all about row reduced echelon form. The last step is pending. The last step is just read the solution. You can check, here are the steps. The first step was just writing into the augmented matrix form. The second step was converting it into row reduced echelon form. The last step was read the solution directly from the row reduced echelon form. How to read the solution? Let's check. Since this column refers to x, this column refers to y, this column refers to z. Okay, so from the first column I can check this 1 times x plus 0 times y plus 0 times z is equal to 1, means x is equal to 1. Okay, similarly from the second column, from the second row, I was talking about row, not column. From the second row, 0 times x plus 1 times y plus 0 times z. In other words, y is equal to minus 2. And from the last column, z is equal to 2. So, I should read row. So from the first row, row 1 implies x is equal to, this is x and this is equal to 1. So x is equal to 1. Row 2 implies this is y is equal to minus 2. And row 3 implies z is equal to 2. And this is how we read the solution after converting the augmented matrix into row reduced echelon form. That's all. Now I will tell you about some cases when we convert our matrix into row reduced echelon form. On the basis of the shape of the matrix, there are some cases. This question is done because we have found x, y and z. This is done. There are some cases, right? We will call them solution cases. The first case is unique solution. When we get unique solution, if in each column we are getting a pivot, okay, not this column because this is the constant matrix. So from the coefficient matrix, In each column, if we are getting a pivot entry, then we will say that the system has unique solution. Okay, and I should write, so if each column has a pivot and there is no contradiction, and there is no contradiction, then we say the system is unique, the solution is unique. Then the system has unique solution. Okay, here is an example. For example, 1 0 0 0 1 0 0 0 1 0 0 0, and here we have 2 3 minus 1 0. You can check each column has its pivot entry and there is no contradiction. If you want to check where is the contradiction, look at the row of the coefficient which is 0. If the row here is 0, here the element must be 0, right? If these numbers are 0 and this is not 0, that means there is a contradiction. Because the last equation will not satisfy then. Since there is no contradiction and each column has the pivot entry, so that means this system has unique solution. What is the unique solution here? X is equal to 2, y is equal to 3, z is equal to minus 1. Because this is x, this is 2, y 3, and z minus 1. Okay? This is the unique solution. The second case is inconsistent solution. Inconsistent system means there is no solution. So this is the similar case. If each column has a pivot entry and there is a contradiction, then the system has no solution. Okay, here is an example. Suppose 1 0 minus 2 0 1 1 0 0 0, and here we have 0, here we have 0, here we have 1. You can check this column has 1, this column has also pivot entry, this column doesn't have pivot entry. So for this, each column may not have pivot entry. So I will just write, if there is some contradiction, then the system has no solution. Okay, so each column may not have pivot entry in this case. Okay, so you can check from the last row. From the last row, the left side is 0 and the right side is 1. This is contradiction. This cannot happen. This is called contradiction. Okay, from the last row, from R3. Since from R3 I am getting contradiction, so therefore the system has no solution. Okay, the last case is infinite solutions. If each column doesn't have pivot entry, if each column doesn't have a pivot entry, for example, if there is a column which doesn't have a pivot entry, then and there is no contradiction, let me write. So if there is a column which has no pivot entry in the coefficient matrix side and there is no contradiction, because if there is a contradiction, then we will say the system is inconsistent. If there is no contradiction and there is a one column, at least one column, which have no pivot entry, then the system has infinitely many solutions. For example, we have this matrix 1 0 minus 3 0 1 2 0 0 0, and here we have 1 minus 1 0. You can check this column has pivot entry, this column has this pivot entry, and this column has no pivot entry, right? Why? Because after this pivot entry, this is the submatrix, and in this submatrix there is no non-zero entry, so that's why there is no pivot entry in this column. Okay, got it. Now you can check that this is x, this is y, and there is no z from here because z is free. So I will say that z is free. If there is no pivot entry in any column, so the variable related to that column is free variable. Z is, because there is no pivot, so we cannot find its exact value. If we are not able to find its exact value, that means it is free. When it is free, it can take any value, so that means it has a lot of values. Therefore, the system has has infinitely many solutions. Okay, so this is the end of this topic.